Hi, I'm Christian from the Customized High Performance Computing Group, and today I will talk about Agile FPGA programming. So where does my fascination about FPGAs come from? And for me, it really comes from the unmatched performance they deliver in currently available computing systems. They are just outstanding in the performance per watts metric compared to widely available alternatives. And also, industry is now getting traction on that. So with the acquisition of Altera from Intel, they push FPGAs into the server market. And just a month ago, they stated that FPGAs are fast becoming the significant accelerator for both web, scale, and cloud environments. And so with FPGAs, we really will see a major transformation in how we program them and how much we use them. And yeah, I've been using FPGAs now for 3-4 years and in similar applications as data centers. And there are really some deep frustration pain points that you have to deal with when you use FPGA in such a setting. The first is integration. So oftentimes, when you use an FPGA, you need high-speed interface. You need DDR3 RAM, you need PCI Express, you need gigabit Ethernet, or any other high-speed interface to get your data in and out. And you're pretty much on your own on many cases. And oftentimes, designing those interfaces can be even more complex than designing your actual system. So that's really frustrating. If you want to get a system up and running, you spend most of the time in integration. That's just big pain point. Another one is synthesis time. When you use big FPGAs, and those are the ones used for acceleration because you really want power, and they are large, they have millions of flip-flops. And to synthesize the design for them can take hours, if not days. I had designs which took several days. And that's just a major pain point. If you have a bug on the device or if you want to change something, that's just an iteration cycle that's not very good for a designer. It really is very frustrating. And also the last one is rigid designs. So FPGAs, that's kind of why they are so energy efficient is that you only put on the chip what you really need. So you don't put stuff on the FPGA that you don't need. So the designs are very much tailored to one specific application and to one specific case even of that application. And you make many optimizations, and you have to do them because otherwise you lose all the efficiency. And with that, the result is that if you have changes in requirements, it's often easier to start from scratch, to throw everything away and start from scratch instead of adapting your very rigid design. And this is also another pain point if you are looking at big data or high-performance computing applications, where you often iterate, you often adapt to change, you have different requirements. You don't know yet at the beginning what you need to do. You explore and see while you're doing things what you really need and what's challenging in your application and what not. And these three challenges are really a major pain point for that and lead to a lot of frustration. There have been some recent innovation to deal with those challenges. I want to point out two. One is high-level synthesis, and this has been really a major breakthrough. If you're not using high-level synthesis, look into it because it has some very big advantages in the design cycles and all the challenges I told you about. It's just you can write, instead of writing VHDL code, you write C code or C++ code without any timing information. And the code is just much shorter, it can be more abstract, you can reuse it more often, and you also have like an estimation tool which gives you some estimations in a few minutes. Still, with high-level synthesis, you don't solve the problem of integration, and also when you ship out the design, you still have the the long synthesis time if you really want to run it. Another one is system-on-chip FPGA systems. We see that from common vendors like Xilinx and Altera. They are now putting more and more ready-to-use hard IP core interfaces onto their FPGAs. They put CPUs on there, gigabit Ethernet ports, and DDR memory controllers, and many other things. And that is very handy because they are really easy to use, and you have much less system integration time. Still, with that, you still have the same challenges in kind of the rigidity and also the other things, and also high-level synthesis and SoC system. They don't yet play so nicely together. So there's still a lot of room for improvement, even that. But we're getting very much closer to that workflow that we're used to in software programming, for example. And what have been some key drivers for me to look in agile methods now, into more agile methods, to even more agile methods? One was really, I'm a very creative person. I have so many ideas and I like to try them out. And for me, I don't like to wait. So when I have an idea, I want to get immediate feedback. And I am somebody who iterates on designs. So for me, an agile flow is really my DNA. It's in my DNA, you could say. So that was the core driver of it. And also another driver was like that I have been working with many different acceleration applications where I wanted to use FPGAs in many different fields. In finance, option pricing and calibration, in big data about social network analysis, and in image processing about industrial product inspection. And dealing with so many different fields, I just had, in hindsight, I could see some things I did always the same, and by that I was able to extract basically and condense the methodology that I've used. Yeah. So let's look at the Agile Manifesto. The Agile software development is really a key term, so there are people really teaching that, and it all comes down to a manifesto, which are basically 10 or I think 11 rules. You can look it up on Wikipedia. I have printed it here. And I have highlighted some of them, so which are relevant for us. Half of them are more related to how to work together in a group. How do we respect each other? How do we work with each other? And the other half of it has to do with how do we use the technology of software. So let's look at that in the terms of FPGA. So the first one is that we reach customer satisfaction by early continuous deliverable of valuable software. Now, continuous deliverable with FPGAs is hard with programming times of 2 days. That's already a challenge. The next one is working software is delivered frequently, weeks rather than months. And if you think about that, it's very challenging to do that with FPGAs. In addition, we have working software is the principal measure of progress. In our case, that would be like a up and running FPGA device in our server infrastructure where we have code running. That's a working software working. And for me, I also tend to say what we put on the FPGA is software, because it's not hardware. We don't buy it. It's not fixed. It's really software. We can program it, reprogram it. It's really the same what we put on the CPU. So also in the FPGA, kind of working software would mean that we have a running system, in my point of view. And the reason behind that is that you really test the real system. You don't make assumptions. You really go to the end in mind, and it's very useful to do that. So I also want to do that with FPGAs, but there integration is really big pain point that's in the way. The last two ones are related to adaptation of change. So one is regular adaptation to changing circumstance. And the other one is welcoming changing requirements from customers, even in late development stages. And that's really horrible for FPGAs. I've told you before, we have rigid designs. When you change something, you have to start from scratch. So that's really not fitting at all. So what can we do instead? And one solution I found is to replace software with concept. So when we do that, when we say, okay, it's not about an up and running system with ready-use software, working software, it's more about a concept. Like you could say like an idea or like written down idea on how we would build it, if we would build it. In that case, we can have continuous deliverable of valuable concepts. We can do that. Concepts are, we can iterate on them as fast as possible. Synthesis time is not relevant anymore. Also, instead of having working software, we look at estimated concepts. So we look at concepts and kind of the key parameter that's interesting for us, like what's the runtime, what's the complexity, what's the cost, and all the different metrics we're interested in. That's what we call with, that's what we replace with working software. We replace it with estimated concepts. And we can do that, we can estimate concepts quite frequently on a week rather than a month basis, because we can use simulation and other things I will show you later. In that case, we can also assure progress by looking at our estimated process. We have them all at hand. We can track the process by having estimated concepts. And also, it's very, very well suited to adaptation of change, because they are not rigid anymore. They are abstract, they're more abstract, and we can change them much more fluidly. So with that, we have tackled all the pain points of FPGAs, and we have found an agile way of doing it. Now let me first walk you through the whole stage, what I've talked up to now, and then we look at some of the interesting questions that come up when you work with concepts, like how do we evaluate them, how do we compare them, how do we iterate on them. That's all what we cover later. So let's keep in mind the flow first. So we start with an application here on the right side, and then I think it's on the left side on your video. The screen is flipped, so bear with me. So we have the application, and the first thing we are doing is we try to get a first implementation or a first concept, either way what's easier. It might even be not on FPGA but on CPU or in MATLAB or very high level software language like Python, to really get a working, the most basic idea to implement something. And that's what we call the depth first approach. And it's really it's really about functional correctness. It makes sure that we understand the problem correctly. And it's not about speed. That's why we can also do it on Python or MATLAB on a CPU. And it's really for us to learn about the application, about the challenges, to get knowledge about that as quick as possible, and to test if we understood everything. And that's really possible in high-performance computing application. That's a different mindset that we have in embedded computing. And embedded computing would do it very differently. But in HPC computing, we normally don't have like very hard requirements on real time or other things. So it's more soft requirements. So something that is functionally correct, you can run it and you can scale it up. You can scale it up to hundreds and thousands of devices, and it will still work. It just takes longer. So it's a good thing to start with, and then you can improve on that. After we have done that, we collect ideas. So when we run through that process, normally ideas come up already. Just that's the way it is. And we collect all of them. And we might even go a bit further and do some literature research on what other people have been doing and collect that as well. And here the idea is really to go as crazy and flexible and vast as you can. And to write them all down. So it's really important to document that at this point. To write them down, maybe make a short list, because we won't address all of them. But it's important that we collect them. And that's also something you might know from a lot of creativity methods, like brainstorming. You normally go into a creative phase where you just collect ideas, as crazy and as impossible as they are. And afterwards you evaluate them in a later stage one by one, because you use different parts of your brain and it just fits better to how we humans work. And we do the same. After that, we use the most promising idea, and we can follow our intuition here. We can say, okay, that sounds like this would make the biggest impact. And then we evaluate and compare it. So we evaluate this new idea compared to the first implementation. And we can even compare it. And we compare it on the highest abstraction level. So we use as little effort as possible. We don't program everything and write on the FPGA. No, we want to just make a decision of, is this worth it? Was this idea worth it? Is this better or not? And we can use, for this decision, we don't have to implement everything. We can also do some abstract thinking. And then the idea is to iterate on that. As fast as possible, as fast as we can, we try out new ideas. We might come up with new ideas after doing that. And we just go through the ideas again and again and again and do iterative refinement. And once we're satisfied, before I go there. So this is what we call design space, kind of all the ideas we collected on how we can do things. This is what we call design space. And here we get different abstract models we can use to make these comparisons. Once we have implemented, or we are satisfied with our efficiency, our metric, we can go to an implementation. So we have now the working concept. It's fully evaluated. We have a good idea on how fast it is, what it will deliver, and now we can implement it. And here's a nice catch. We have not only a concept, but a concept that has been estimated, evaluated, and where we have extracted some metrics. We know something about this. So we can use that knowledge to guide our implementation. So we can check if our concept says this runs 10,000 options per second and our implementation only achieves 10, something is wrong in our implementation, maybe, or something is wrong in our abstract model. But we can be mindful about that, and we can use different objectives to guide our implementation. And we will look later into some real examples about that. So the first question, really the most pressing question, is how do we compare concepts? That was really the key. So, okay, it's not the best way to do that, really. Okay, great. So, this is kind of the loop we are always doing, like this. And for that, we need to compare concepts, either to the first one over here, or to the last one, or to previous ideas. So how do we compare different concepts? And here we use different abstract models. And let's run through an example. So when you use FPGAs, you have different choices. So I give you two. When we have a hybrid system, we can either choose if we put a core, a computational task, if you could say, on the FPGA or on the CPU. It might be too big for the FPGA, it might be too slow or too expensive for the CPU. You have these options. And also sometimes when you process data, you can either store it in memory or you can stream it through the FPGAs. You can build a streaming engine or you can build like a load store engine. And these designs will have different pros and cons. And to evaluate which one is quicker, you often want to know kind of how big is it on the FPGA if I do it one way or the other. Which will also give you some hints on how fast this will be. If you go for it, if you fix the frequency, you also know how fast it is, and if you know how the engine works, by knowing how big, how large it is, and how many devices you can put on the FPGA, you know how large, how fast it can be. So FPGA area estimation is really, really key in designing FPGA and evaluating FPGA concepts. So let's run through different abstract models. And the abstract models are really iterative. So we start with the most abstract model we have, and then we go down, abstraction layer by abstraction layer, we go down, until we reached a sufficient enough, you could say, estimation to make a yes or no decision, which one is faster. If two concepts are very close together, we have to go really deep into our abstraction layer. If one idea is clearly better than another, we can stop already at the highest abstraction layer. So what are these for FPGA area estimation? So the first one, and that's in most estimation, is starting with thinking, starting with paper estimations, not even programming anything on the FPGA or on the CPU, but to really just do a paper estimation. So we could count the number of operations, we could draw an architecture, we can choose the parallelization, we can look up resources in data sheets from previous designs, similar designs, and also look at how much is an adder, how much is a square root, how much is a multiplexer, and we can kind of come up with an estimation of basically a list of things that we have to include. And of course, this is just a crude estimation, but it's a starting point, so why not? The next one is HLS-based backed estimation. So in that case, we say, okay, paper estimation was too crude. Let's look at HLS and program some blocks, the relevant blocks, not our architecture. Maybe there's only one big block. Everything else is like little state machines, which make it very complex, but not relevant for area-wise. So we only program kind of the area-heavy things in HLS. And we also might simplify these designs. So we might leave out details and things that don't impact the area. And then we synthesize it, we simulate it and get an estimation about that. So we might only simulate the data paths or ignore state machines, ignore small blocks. Use HLS, and then also we might adjust for an overhead just based on intuition, based on experience. And we later see that experience is really important for that. But let's keep in mind for now. And the next one is synthesis-backed estimation. So HLS will give us an estimation, but we also can synthesize it. So we do the same and we synthesize it for the FPGA and see if there's some difference. Oftentimes we have, for example, wiring overhead, and HLS is also not so good at estimating that. So if we have wire congestion, we really need to do a place and route. So maybe does that change something in our block? If we already know, oh, there's a lot of routing congestion, let's implement that block and see how big is the overhead for that block. Then we can do even more. We can do VHDL enhanced estimation. So you know that sometimes in HLS, if you have used it, you cannot model everything the way you want it. Sometimes there's just an overhead in kind of the way you describe things. So in that case, we could model these things that are not very suitable for HLS, like control logic. If we have complex control logic, like small control logic, which we have thousands of times in our design, which is sometimes the case, we can say we use VHDL for that. So we program this kind of control logic in VHDL, the rest, the data paths in HLS, and then we put everything together in one estimation. Next step is kind of, and you can have more layers. This is just an example. So the next step could be you have a full VHDL implementation, HLS implementation, combined implementation, It runs, you synthesize it, you implement all the blocks and state machines and everything, and run the block on the FPGA board. And the last thing is really to run the full application. So if you, for some metrics or for some area estimations, we just need to run the full thing on the board to really see, does it work? The frequency maybe. Does the frequency work? If we want to really play at the edge of our FPGA device, to really go at 200, 300 megahertz, maybe even more, 400, 800, then and play with some interfaces on the FPGA board maybe, we have to do a full application on board. Previously, we can also do like specific cores on the board. Like we can say, okay, the communication interface to memory. We cannot simulate that. We cannot estimate that. Let's make a simple block that estimates that with a very simple state machine or a very simple pattern that might be that's similar to what we use later, but it's not the full application. So we can also play on that abstraction layer. So what you get here is we use different abstraction layers very deliberately, and we also combine them. So you can use paper estimation on one part of your design, VHDL on another part, HLS, very crude estimation on another part, and maybe you have a core which you run on the board for a fourth part. That's the idea of these abstract models, to get really creative in these abstract models and save a lot of time by doing that. So we trade off creativity with time. And that's something I'm really passionate about. So how do we find these abstract models, you might ask? Okay, I've given you now these very, very advanced, very, very good abstract models, and you might even think like, are they really so good? So first of all, how do we find them and how do we use them? And two important questions are really, can we trust our models? Is it accurate? And is it valid? What was the second? What are the limitations of our models? We really have to know that. How accurate is it and what are the limitations? And for that, we have to build up experience. So we have to work with these abstraction layers. So we have to do, for example, paper estimation. We cannot, when you go to a really complex design, you cannot start with paper estimation. You have to make it part of what you do on a daily basis in every design. You always start with paper estimation. And then you will learn what the pros and cons are. And you start with simple things, like when you learn a new technology, like, okay, well now we have HLS, and now we have Sync, and now we have FPGAs. You never worked with that. What you do first is you use very simple examples. That's what you do when you learn anyway, and that's how you build up experience. So you work with simple examples with the technology and the abstractions layers you're interested in. Like paper estimations. Try to make a simple paper estimation of a crossbar. That's a very simple design. You can write it down, you can see the numbers, and you can compare it with maybe a block from Xilinx, which is already implemented, and see how close is it? How good is my paper estimation? And if you find out, it's not good, why is that? What's the limitation? Is it that I forgot something, that I didn't consider something, or is there some other effect, like routing effect and a placement effect? So you really have to work with these models. There is no way around it. But the good news is we can do it on simple designs. And we don't have to do it on our complex designs. Yeah, so we really have, I want to stress that one more time. What's really crucial is that we have a deep, deep understanding about the technologies we are using. Everything. FPGAs, how do they work? What do they function? How? Also compilers, like how does place and route work? How does mapping work? What problems can happen in mapping? What's easy to map? What's hard to map? Also in compilers like VHDL, how is the mapping between VHDL and logic? Also when you use high-level synthesis, what are the pros and cons of high-level synthesis? What is easy, what is hard? And also even paper estimation. What What is hard to estimate in paper? What is easy to estimate in paper? You really have to deeply understand the technology and the tools you're using. And you can do that. You have to dedicate some time for that. So just by programming FPGAs, you will not get that deep understanding. You really have to dig into the tools, into the FPGA designs, how do they work. And it pays off tremendously. So for me, it has paid off. I invested like a week or 2 weeks in learning how FPGAs work and really trying. You can try little things like, okay, the data sheet says a lookup table has this kind of function, and you can play around. Hey, does this work? You can test. You can also test you have to test your knowledge. So that's really the first part of using agile and abstract methods, is to really get a good model and a model in your mind about how it would work, how the compiler would do it. So you have to know the whole process. You must be able to run through it in your head. I hope that was helpful for you, because this is really the hardest part to teach. And yeah, if you have questions, put them down in the comment. I can help you with specific designs. Write emails to me or to my colleagues. We're really passionate about that, and we really like to brainstorm even about ideas on how to do that. So let's go to the next. Objective guided optimization, we said. Implementation, we said. So once we have our concepts, when we say, okay, the estimation is good enough, we want to implement it now and run it, we can use different objectives. And here are just some examples. They could be resources. As I said before, we have these abstract models. We know the number of adders, the number of multiplexers, the number of BRAMs, the number of LUTs, whatever we estimate. We can check that with the implemented design. So we estimated 2,000 flip-flops, and now our design takes 10,000. There is a mismatch. So we look closer at it. An objective guided implementation is really, really a saver for you, because it guarantees that the effort you have made in your concept will translate into your designs. So don't put that lightly. This is really a key part of the methodology. And if something is not working out here, you either can do a better kind of programming, a better kind of implementation, or you have to go back to your abstract models and re-evaluate the choices you have made. But either way, it's a good feedback. And also, if you compare that to traditional software development, I think it even has an advantage to do it like that. And I would even stress that if you are just doing a MATLAB design or a CPU design, I would still work on concept and abstraction. I would still follow the same design flow, because when you do software programming and you optimize, for example, a program for a CPU, you have let's say you have a random number generator and you want to make it as fast as possible on the CPU. What do you normally do? You implement it in CPU, you run it, okay, you get a certain speed. Then you think, okay, what can I optimize? Yeah, this and that, this and that, this and that. You try different ideas. Okay, maybe it's 2 times faster or 10 times faster. But who tells you if you reach the limit? Maybe there's another 10x speed up that you are not seeing. Or you can already tell, like, we are close at 1% of the peak performance. You cannot get better. You're wasting just time. You're trying different ideas and there's no way of getting better. And with these concepts, we get a good understanding of how close we are, how efficient we're using our hardware, our CPU, for example. You can even apply it to CPU. When you have a deep understanding about how the CPU works, how assembly works, how the compiler works, how high-level languages works, you can do the same. And it's very powerful. And people do that. So you might have heard of people talking about how close you are to peak performance. And that's one objective guided implementation. How close are you to peak performance? And I think we have that over, I'm not sure. Yeah, so we have different objectives. I think you can see them. So utilization, CPU, memory, throughput, frames per second, and so on. For the CPU, we can also have kind of the instruction parallelism or instruction per second. so different metrics here. And also for GPUs, you can say how close are we to peak performance and so on. Yeah, so let me just check in. So we now covered concepts, the design space, how to iterate on concepts, and we also talked about how to use abstract model, how to compare them, what abstract models are, how you come up with abstract models, how you use the abstract models to guide the implementation to achieve the same result in reality. One thing that came up when I designed FPGA designs was the following scenario, and keep in mind with me. So when you have two concepts, two ideas, and I will make an example. The idea could be that we offload a task. So for example, we have an image coming into our device, for example, image processing, an image comes in, and you can either process it on the CPU, or you can send it to the FPGA, process it there, and read it back. And now it depends on the size of the image. If the image is really small, like 4 by 4 pixels, the CPU will be much faster. It will just tuck, 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 it's done. Rather, by sending it to the FPGA, there are some delays in that, doing the data processing, data transfer. But if it's a really large image, like 10 megapixels or something like that, the data transfer will get negligible, and the processing on the FPGA side will keep up. So in that case, this idea depends on kind of the specific situation we are in. So we cannot tell it. And we have three things normally what we call for trade-offs. Trade-offs is always when you have two choices. So in that case, we only have two, but you can also have more. So when you have more than one choice, we say this is a trade-off you can make, putting it on the FPGA or the CPU. And you have three types of trade-offs. The first one is always better. So maybe idea number one is always better. And we have a lot of trade-offs are like that, and it's a good one. Or we can have like it's never better. It's like always worse, and we never use this kind of new trade-off, this new idea. Okay, great. But sometimes we have this in-between, it depends trade-off. What do we do with them? Do we now have two concepts? How do we deal with that? And what I realized is we can do a trick here. We can say we capture all of that. We say we don't make the choice now. We make the choice later when we have the information. So why should I do the choice now? Later, I know, once I have the image on the CPU and I know how large it is, I can decide if I send it to the FPGA or the CPU. And that's what we call a platform-based design methodology. And it's a term originally coming from microelectronic systems, but we also can apply to software systems. So it's like the following concept. It says we have an application space, we have flexibility in our application. So in our case, it would be like the size of the image changes. It's not always the same. It has a flexibility in the size of the image. And also we have the platform changes. Like, you know that on the sync or on the different FPGA devices, when you have a data center, you might have different sized FPGAs, different kind of speeds of the interconnects. And you have flexibility in the architecture. And also depending on that, you might want to do different choices. So you also capture that, the flexibility in the architecture, you capture also that. And the platform then, once it has a specific instance of the application space, like, okay, we get an image, 10 by 10, and we know on which platform we are. We're on a small FPGA with very low latency. We can make a choice and say, okay, now we send it to the FPGA. That's what the platform is doing on runtime. So instead of building implementations, we build platforms that always generate us the best way of doing things in the future. So these things we call trade-offs that we put in the platform. And now the really cool thing here is that we can use the abstract models to build our platforms. Because in the abstract models, we are doing the same thing. We want to decide which idea is better, right? We want to say, is it better to offload a task to the FPGA or keep it on the CPU? We already modeled that. We made some paper estimation. We have some equations for that. Maybe we have, if based on bandwidth, based on latency, we can make a decision. We can create a formula. And that's what we can use before on paper, we can use to automate and put directly into our platform. So it nicely feeds back into our methodology to handle this kind of flexibility. Yeah. And with FPGAs, I learned that platforms is really what you want to do. You don't want to build a generic FPGA bitstream or FPGA software, because as we said before, the advantage comes from putting on the FPGA only what is really needed in that moment of time. We can reconfigure it, right? It's a reconfigurable device, so let's use that property. In that case, we want to really have different bit streams depending on what we have there. And the platform is exactly the thing that will generate us different bit streams for different cases. And we can also put that in the platform. And we also made a video about that, about a platform we created with this kind of methodology, with different automation systems. And there's also a MOOC about that in a previous episode. So if you're interested in that, check it out. It's really good. Another thing I want to point out, so now we have covered quite a bit in our design flow. We have tackled all the agile challenges. We talked about concept, how we iterate on them, how we handle flexibility, how we use the generic properties of the FPGA of reconfiguration, how we put that into our methodology. And now I really want to scale it up. So we don't want to think only about, okay, I have to do the whole design. But if you go really to HPC designs, you want to build in big design teams, interdisciplinary teams. And I will now make some points on how to use this methodology in this setting. Interdisciplinary teams. This is really cool. We have done that. We have talked to mathematicians, to people from computer science, from people from industry with a lot of domain knowledge, but not FPGA knowledge or programming knowledge. And we have integrated them into our process in the following way. You can show them concepts, and you can show them the concepts on a very abstract level. Like you've estimated them on an abstract level. You can talk about these things in a language that they understand. You can abstract from all the details. You don't have to give them the code. You can just tell them on an abstract way what the architecture is doing in a simplified way. That's enough. That's sufficient to explain the whole thing, right? So it's really easy to communicate when you have a good abstract model and a good understanding about, about the thing. And also you can use the meetings to brainstorm ideas. You can say, okay, here's our design space, here's our flexibility, here's our application, that's where we are, that's where we want to go. Do you have any ideas? And you can even see, you can see the skills you need. You can say, oh, we don't have a good abstract model right now to estimate memory probability or memory things. What do I mean? Memory behavior, DRAM behavior. We don't have a good model for DRAM behavior. So let's find an expert in DRAM simulation and talk to him about that. Or you might feel like the application is still too slow for our use case. We need new ideas. Let's talk to some algorithmic people or to some implementation guys if they have new ideas. Or you can say, we don't really understand the technology. Let's seek out some expert in the technology domain and explain us the technology. So you really know where you will lack expertise, and you can communicate and directly go to these experts and form very powerful interdisciplinary teams that are really suited to what the project needs in that specific time. Also the meetings. You can use the meetings to share the design space, the models. You can communicate that, you can document that, you can share new flexibility, new ideas around that, because the concepts are really easy to communicate. And also, it's everything is kind of documented what's in there, and that's really the power of the Agile method. that we iterate on working things, and for us it's working concepts. So if I leave tomorrow, you can still build on that thing, and yeah, we don't have to understand everything to build on something else. It's really, we have modularization, we can make decisions, high-level decisions, we don't have to understand everything. And that's really good for meetings to also follow that flow. You can also do brainstorming in these meetings. This is really, we have done that several times with students and also other colleagues and people from industry. We just brainstorm, we say, okay, this is what we have. Do you have any ideas? Let's collect them, let's meet, let's brainstorm for 2 hours and then meet and collect all the ideas, and maybe the new ideas come up. So it's a really creative place, and yeah. Also, it's about team management. So when you manage a team, it's often difficult for the members or for management to just to integrate the different efforts people are making. And for that, in the Agile flow, it's easier, I would say, because you know, you get like weekly updates, weekly working concepts. So you can really track, okay, does he have all the information he needs? Is there a problem? Is he making good progress? How can I support him? So it's very transparent on where people are struggling and where people are making progress. So it's easier to manage people in that way. And to support the team, and also the team itself, it kind of knows, okay, hey, they can talk about that. They get feedback also for themselves. They will know, oh, couldn't estimate that this week. It was really difficult. And they might tell a colleague, hey, I have a really problem on estimating that, and he might have an idea. So it's also good for the members of the team itself. Okay, so with that I want to conclude this MOOC and summarize what we covered. So today we covered how to do Agile FPGA programming, and as I have said, this is not limited to FPGA programming. You can also use it for ASIC programming, you can use it for hybrid system, you can even use it for CPU only system, as I have said before. Everything applies. It's just another way of doing Agile methods. And I've explained it on an example of FPGAs. With that, we can maximize really our creativity. So instead of just surrendering to the hard integration, to the long synthesis time and the rigid designs that we all have to start over from scratch, we get creative, we get smarter, we hack the system basically. We hack the system and we get creative, and we get back the speed we want by investing in knowledge and into abstract models and using higher level comparison methods and doing our flow on a high level. And we have seen that. So all the tools, they're not worthless. The tools really help us. So we can integrate all tools there are, many different tools, like all the facets of tools there is, paper estimation, simulation, VHDL, HLS, and even many more for different parts of the system. So we can really integrate all the tools we have into powerful hybrid abstract models that are really creative and really fun to play with, and that are really it's really fun to play with concepts on that scale, at least for me. That's why I'm so passionate about it. The next one is we looked at iterative abstract models and newest technologies. So I gave you specific examples on how such a abstract hierarchy looks like and how it integrates different technologies. And we looked at also how to handle flexibility in concepts when you evaluate concepts, like sometimes it's not clearly better, and you can use both concepts and you can trade off between them during runtime with automation and building platforms. So with that, thanks for listening. And I really hope that this was helpful for you. If you have any interest in that, contact us or comment below or share your success stories. We're always happy to hear other people benefiting from that. And there is this Hyper project. You can also check out the video. There's code for it. There's also a lot of documentation on how to set all this up. So those are all pointers for you to dive deep. And I would really ask you to try this out. Try this out in the next project, maybe not on the largest project, maybe a smaller project, or just like the next time you learn a new technology. think about this technology and apply it. And I would ask you to make a decision today. Like, make a decision today on where you want to use that. So oftentimes we watch videos and we never use that knowledge again and forget it, and years later we go, oh yeah, there was this guy. And so I want you to make a decision today to serve really you, to decide, do I want to use that? Is that a hell yes for me, or is that maybe? If it's a maybe, forget it, you will never do it. Decide if this is a hell yes, if this sounds interesting, and if it does, make sure you're using that. You commit to a project or an example or kind of a day in the next week. You're trying out this on a real example you're using. With that, thanks for listening and see you in our next episode.